Hello everybody, my name's Matthew Mould. I'm a first year PhD student at the University of Birmingham here in the UK. Thanks for listening to my talk here at the LISA Symposium 2020. I'm going to be talking to you about unstable spin precession in binary black holes and the prospects for its detection. This work was completed with my PhD advisor Davide Gerosa and was published in Physical Review D. It's also available on the archive. So we'll begin with the general picture of a binary black hole with our conventions on the left. And for arbitrary masses and spins, there are three angular momenta associated with this binary. So there's that of the two black hole spins, S1 of the primary heavier black hole and S2 of the lighter hole, and the orbital angular momentum. And in general, the dynamics of these angular momenta are very complicated due to interactions between each other. And this is important from a gravitational wave standpoint because it leads to spin precession, which modulates the detected waveforms from merging black holes. So you can see these severe amplitude modulations in the waveform for a precessing binary compared to the more typical chirp signal we see from a non-precessing binary. And the simpler configurations which produce these non-precessing signals are the aligned spin binaries. So in these configurations, the black hole spins are either aligned or anti-aligned with the orbital angular momentum. And there are four possible configurations for unequal masses. And here we use the direction up to refer to a black hole spin which is aligned with L, and down refers to a spin which is anti-aligned. And in each of these four configurations, the direction before the hyphen refers to the heavier hole, and after the hyphen refers to the lighter hole. So the question we want to answer is, are these configurations stable? In other words, if we perturb these exact alignments slightly, how do the spin vectors behave? And we'll measure these misalignments with the tilt angles θ1 and θ2 between the spins and the orbital angular momentum. So to do this analysis, we'll use this multi-timescale post-Newtonian framework. So namely, in the dynamics of binary black holes, there are three separate timescales to consider. There's that of the orbit, there's that of the precessional cycles, and there's that of the inspiral. Now in the post-Newtonian regime, when the black holes are sufficiently separated, these timescales are separated so that we can study each part of the dynamics separately. So this first inequality, namely that the orbital cycles occur much more quickly than the precessional cycles, is at the very foundation of the post-Newtonian framework, and from it we can produce the orbit-averaged spin precession equations. And so our problem primarily consists of three spin vectors, so we have a 9-dimensional problem to consider, and this can be quite complicated. However, there's a lot of dimensionality reduction we can do. So firstly, the two spin magnitudes of the black holes are conserved. And secondly, we can choose a reference frame, so we can fix L in our vertical axis and S1 to lie in one of the planes of our frame, and this corresponds to removing three extra parameters. And also there's this conserved quantity, the effective spin, also known as chi effective in the LIGO literature, and so this reduces our parameter space to just 3. But finally, considering this extra inequality, namely that the precessional cycles occur much more quickly than the inspiral occurs, then over the precessional timescales there are two further conserved quantities, namely the magnitudes of the orbital and the total angular momenta. And so this is remarkable because it reduces our parameter space to just one variable. So the dynamics is completely characterized by a single time varying quantity, and one convenient choice is the total spin, S. So on the precessional timescale, the dynamics is governed by this evolution equation here, which is solvable explicitly in terms of Jacobi elliptic functions. And so this, for example, can be used to produce waveform models. But in our study, we're actually going to focus on the ODE rather than the solution. And in particular, we're going to differentiate it once more and rearrange it in terms of a perturbation to our aligned configuration. So here, S star refers to the total spin of one of our four aligned configurations, and so the quantity s squared minus s star squared represents a perturbation to one of these configurations. And what we find is that to leading order, these perturbations obey the equation for a simple harmonic oscillator. And so the question of the dynamics of the system becomes very straightforward. It's entirely dependent on this oscillation frequency omega. So when it's real, we have stable oscillations around the aligned configuration. But if it becomes complex, then this introduces a instability into the dynamics. So omega depends on which of the four aligned configurations we're talking about. So when you plug in all the relevant values, what you find is that three of the configurations are stable, however one is unstable. Namely, the up-down configuration encounters an instability at a critical orbital separation given by this expression here, at which the oscillation frequency transitions from being real to complex. And in terms of the dynamics, this corresponds to a transition from stable small amplitude oscillations around the exact alignment, as seen in this movie here, to an unstable out-spiraling of the spin vectors due to spin precession, leading to large misalignments. So how does this instability evolve? Well, our original equation here is only valid in the small perturbation limit. As soon as we encounter the instability, this is of course no longer true, so that equation no longer describes the dynamics post-instability. So instead we do direct numerical integrations of the post-Newtonian equations of motion. What we find is that for a selection of up-down binaries, initially represented by this blue histogram, we evolve them down to smaller separations represented by these orange histograms. So they start at the smallest possible total spin magnitude, because the two spins are cancelling out, but they tend to the maximum allowed possible spin magnitude. And going from left to right in these panels, we're increasing the initial perturbation of the configuration. And what we find is that rather than dispersing in the available parameter space of our variable s, in all of these instances, the unstable binaries are clustering to this exact endpoint. So how can we describe this? Well, it turns out we can describe it in terms of spin-orbit resonances. Now, these are binary configurations in which the three angular momenta are coplanar, and they remain coplanar during the evolution. So this coplanarity condition corresponds to this angle delta phi, which measures the separation of the in-plane spin components. It's either 0 or 180 degrees for coplanarity. Now we can, skipping some details, we can derive an equation to locate these resonant configurations. And this is crucial because the up-down configuration is one of these resonances prior to encountering the instability. And so this equation is a fifth degree polynomial in j squared. So if we want to locate the endpoint of our up-down evolutions, we can simply take the zero separation limit of this equation. Now this is an unphysical limit, but it does identify the asymptotic limit of our unstable binaries. And what you find is that these unstable up-down configurations tend to this delta phi equals 0 resonance, corresponding to a maximized total spin magnitude, which we predicted with our numerical integrations, and tilt angles, which tend to equality and are given by this expression here. Now we can verify this again with numerical integrations. Here we take a LIGO-like population with the set of mass ratios distributed according to the O1 and O2 catalogue. So in these two panels we have our initial set of binaries at a larger separation, with the up-down subpopulation given in red, and the other three aligned configurations appearing in the other vertices of this panel. We integrate them down to a smaller separation, and we notice that our stable configurations, the up, down, down, and down, up binaries, remain close to their initial alignments, whereas the up, down configuration splits bimodally. So we have those binaries which remain stable and those which are very clearly become unstable. And of the unstable subpopulation, we find this very clear trend along the diagonal, and this precisely agrees with our prediction of equal tilt angles. So onto the question of detectability. The good news is that we find that this instability develops over a short timescale, corresponding to a decrease in the orbital separation of 25 total mass units. So what this means is that for our LIGO-like population, most of the population reaches our predicted endpoint before entering the detectable band of the detectors. And these unstable binaries are given by the black dashed histograms in these panels. Those binaries which remain stable, given by the grey histograms, are mostly contributed to from binaries which have low spin magnitudes. However, in practice, the best measured parameter from waveforms is the effective spin, so chi effective for LIGO. And with this parameter, unfortunately, our unstable up-down subpopulation is not distinguishable. Again, it's given by the black dashed histogram in this figure, and the stable binaries are given by the grey dashed histogram, and there's no distinguishing features between the two. And even worse is that for the LIGO-like population, which strongly favours equal mass binaries, it's also difficult to distinguish between the down-up and up-down configurations due to their symmetry for equal masses. However, another tantalising possibility is to observe the development of the precessional instability while a binary is in band. So this would correspond to a binary, an up-down binary entering the detectable window whilst it's stable and becoming unstable whilst being observed. However, we estimate this is a very small fraction of a population of that LIGO-like sources would be possible. And this is mainly because for LIGO, binaries are only in band for a few orbital cycles, and really we need to observe several precessional cycles to detect an instability, to detect growth in our precessional instability. And this is where prospects with LISA might be better than LIGO, and this is primarily due to the fact that sources can remain in band for much longer than compared to LIGO. But to make any firm conclusions, we'd need a more in-depth study on the detectability of precessional phenomena with LISA. So here's a summary of everything that I've said. So firstly, up-down binaries are unstable to spin precession, and this instability drives binaries to very predictable endpoints. However, to measure this effect, we will most likely need to be able to detect two-spin effects accurately in emitted waveforms. So some ongoing work related to this topic is firstly that this is a post-Newtonian study. So all the analysis and numerical integrations rely on post-Newtonian techniques. So at the moment we have some numerical relativity simulations on the go to see if this instability is present in such a simulation, and the prospects so far are looking good, and we expect these simulations to be finished relatively soon. A second question to ask is that we perturb just the aligned configurations, but we could perturb all resonant configurations and ask whether these also behave like harmonic oscillators. And a final point to note is that all the numerical parts of this work were conducted using the Python package called precession, and at the moment we are creating a new implementation of this package with several updates which speed the code up greatly and has some enhanced features that have come out of this work. So thanks everybody for listening, and be sure to send me questions on my page if you have any. Thanks.